In this video, we're going to be talking about 7.3.2, which is the second translation theorem for Laplace transforms, and that's translations on the t-axis. So let's go ahead and get started here. 37. Actually, before we get started, let's do a few definitions here. So when we take the Laplace transform of the unit step function of t minus a, that's going to be equal to e to the negative as over s. And when we take the Laplace transform of f of t minus a, unit step function t minus a, where these match here, that's equal to e to the negative as capital F of s, as if whatever this function is before it was shifted is what that capital F of s is. So we'll look at that in a second, and hopefully that makes more sense once we do that. And if we have Laplace transform of g of t, unit step function t minus a, where these functions don't match one another, then that's going to be equal to e to the negative as Laplace transform of g of t plus a. This is actually the general rule here that works for all of the functions, but these are two special cases that we're going to be using quite a bit here. So, so you could be writing this as Laplace transform of f of t, because this got shifted a, t minus a plus a is f of t, and that is just denoted as capital F of s. All right, let's start with number 37 in the textbook. And going to have Laplace transform of parentheses t minus 1, unit step function t minus 1. So we're going to be using the second rule here, is equal to e to the negative as. And then this is going to be Laplace transform of t, which is going to be 1 over s squared. So that's going to be over s squared. (39) is Laplace transform of t times unit step function of t minus 2. It's going to be equal to e to the negative 2s times the Laplace transform of t plus 2. So that equals e to the negative 2s times the Laplace transform of t plus 2 times the Laplace transform of 1. This is e to the negative 2s times 1 over s squared plus 2 over s is e to the negative 2s over s squared plus 2e to the negative 2s over s. Let's look at number 41. It says the Laplace transform of cosine of 2t unit step function of t minus pi is going to be e to the negative pi s, Laplace transform of cosine of 2 times t plus pi e to the negative pi s, Laplace transform of cosine of 2t plus 2 pi. We know the period of cosine is 2 pi, so this is Laplace transform cosine of 2t. They're the same thing. So that makes this s over s squared plus 4 e to the negative pi s. Now for some inverse Laplace transforms of this type. 43 is going to be inverse Laplace transform of e to the negative 2s over s cubed. So that's going to be 1/2 inverse Laplace transform of e to the negative 2s times, and I need to write something here that is an f of s. That's why I'm getting that 1/2 out there. It's going to be 2 over s squared plus 1. And so because I multiplied by 2 on the top, I multiplied by 1/2 on the outside. This is 1/2 inverse Laplace transform of e to the negative 2s times the Laplace transform of t squared. So this is 1/2. And then we have t minus 2. That's my t minus a unit. And then this is squared, because that's what that function is. Unit step function t minus 2. That's my t minus a again. 45. Inverse Laplace transform of e to the negative pi s over s squared plus 1. So make that inverse Laplace transform e to the negative pi s times 1 over s squared plus 1 is inverse Laplace transform e to the negative pi s times Laplace transform of sine of t, which is going to be sine of t minus pi, unit step function, t minus pi. I have a sum difference identity for sine that I'm going to use now. So that's going to be sine of t cosine of pi minus cosine of t sine of pi. So my unit step function, t minus pi, and sine of pi is 0, and cosine of pi is -1, so this is negative sine of t, unit step function, t minus pi. 47 is inverse Laplace transform e to the negative s over s times s plus 1. And so we're going to have 1 over s times s plus 1 is equal to a over s plus b over s plus 1. So I have a times s plus 1 plus bs is equal to 1. A plus b equals 0, and a equals 1, which means b is negative 1. So that gives me inverse Laplace transform of e to the negative s times 1 over s minus 1 over s plus 1. So this is going to be inverse Laplace transform of e to the negative s times 1 over s minus e to the negative s times 1 over s plus 1. It's going to be inverse Laplace transform of e to the negative s times Laplace transform of 1 minus inverse Laplace transform e to the negative s times Laplace transform of e to the negative t. So that gives me this one here is, I actually don't even need this piece here. This, by definition, the first one that we did, that's the unit step function t minus 1. And then this is unit step function t minus 1 minus, and then this is going to be e to the negative, and in place of the t goes t minus 1, since my a there is negative 1, and then unit step function t minus 1. And I'm going to skip ahead a bit to number 55 now. There's some important graph problems in between that you might want to try, but I don't want to draw all the graphs on here as examples. So I'm just going to do some piecewise defined functions that are defined this way instead of with the graphs. So 2, negative 2, 0 less than or equal to t less than 3, and t greater than or equal to 3. So we have another rule that says that when I have a function like this that I want to find the Laplace transform of f of t, where f of t is piecewise defined, that's going to be my f of t minus f of t unit step function t minus a, where this is my a, plus my g of t u of t minus a, and this is for where it's just G H is how they define this in the book, because F is already used up on that side, and this is A. So if F of t is this, then Laplace transform of F of t is equal to, and you can define it with the unit step function like that. So let's go ahead and do that with number 55. So my F of t is equal to, as I said before, this is 2 and -2, 0 less than or equal to t, less than 3, t greater than or equal to 3. So my f of s here is going to be equal to 2 minus 2 unit step t minus 3 plus a -2 is minus 2 unit step t minus 3. Those are like terms, so let's add them together. That's 2 minus 4 unit step function t minus 3. Sorry, this is not the Laplace transform yet. Got a step ahead of myself. That's f of t. That's just another way to rewrite that piecewise defined function with the unit step function instead. And now I can find the Laplace transform of this. And so this is going to be 2 over s minus 4 over s e to the -3s. All right, my f of t is equal now in 57, 0 for 0 less than or equal to t less than 1, and t squared for t greater than or equal to 1. So my f of t is going to be equal to t squared unit step function t minus 1. So my Laplace transform of f of t, which is going to be equal to capital F of s, it's going to be equal to e to the -t, Laplace transform of t plus 1 squared is equal to e to the -t times Laplace transform of t squared plus 2t plus 1 is equal to e to the -t times Laplace transform of t squared is 2 over s cubed. Laplace transform of 2t is 2 over s squared. Laplace transform of 1 is 1 over s. So this is equal to 2e to the -t over s cubed plus 2e to the -t over s squared plus e to the -t over s. Let's look at number 59, and then we can go on to some initial value problems after this. T is equal to t and 0 0 less than or equal to t less than 2, t greater than or equal to 2. So f of t is going to be equal to t minus t unit step t minus 2. So capital F of s is going to be equal to 1 over s squared minus e to the negative 2s Laplace transform of t plus 2. So that's going to be 1 over s squared minus e to the negative 2s Laplace transform of t minus e to the negative 2s Laplace transform of 2, which I'm going to pull out the 2, make that 2 times the Laplace transform of 1. So this is 1 over s squared minus e to the negative 2s times 1 over s squared minus 2e to the negative 2s times 1 over s is going to be 1 over s squared minus e to the negative 2s over s squared minus 2e to the negative 2s over s. Let's go ahead and skip down to number 63, which is an initial value problem. Y prime plus y equals f of t, where y of 0 equals 0 and f of t is defined as the piecewise defined function 0 for all t greater than or equal to 0 and less than 1, and 5 for all t greater than or equal to 1. So when I take the Laplace transform of the left-hand side, I get s capital Y of s minus little y of 0 is capital Y of s is equal to Laplace transform of f of t is going to be, let's figure out what f of t is first. It is 5 times the unit step function of t minus 1. So when we Laplace transform that, it's 5e to the negative t over s. For that side of the equation. And so this is going to be s plus 1, capital Y of s. That was 0 is equal to 5e to the negative t over s. Capital Y of s is equal to 5e to the negative t over s times s plus 1. So this is off to the side over here. We have a over s plus b over s plus 1 is equal to 5 over s times s plus 1. I don't need the e to the negative t part because that's just going to be a constant multiplier. So a plus b equals 0, a equals 5, b equals negative 5. So capital Y of s is going to be e to the negative t times, then we have 5 over s minus 5 over s plus 1. So this is capital Y of S is equal to 5e to the negative t times 1 over S minus 5e to the negative t times 1 over S plus 1. So my Y equals 5 times unit step function here of t minus 1 minus 5 times e to the negative t times Laplace transform of e to the negative t. Y equals 5 unit step function t minus 1 minus 5 e to the negative t minus 1 unit step function t minus 1. And then they're going to factor out what's common here and call this unit step function t minus 1 on the right with 5 minus 5e to the negative t minus 1. All right, I think that that's probably enough of that. We have more examples with word problems and circuit analogs and spring problems and other applications like we've done before with this that are great examples to look at if you're going to be in engineering. But this just gives you an idea of what the unit step function is. It's basically a function that helps us if we have a system like a circuit. Is a really good example where you turn the power on or off after a particular time so that you have two different states, your state where you're on or your state where you're off, or anything where you have two states where it changed at a particular time, but it stayed the same during those two things. So really any piecewise defined function can be written with this unit step function, and then we can, as we saw there, and we can use our Laplace transforms of our unit step functions to help us solve these differential equations in terms of those, like we just did in the last couple of problems. So that's gonna wrap up our discussion for 7.3, and I'm going to start talking about some stuff from 7.4 next time, starting with 7.4.1, which is the derivative of a transform. So I'll see you for that next video.